Hello, everyone. Good seeing you all here. Thank you all for joining us. This is a great challenge today for the Spaceport Project Critical Design Review. So essentially just what this is, like I'm sure a lot of you have heard, we're just going to go through the entire design of the rocket, every subsystem, and kind of give a nice descriptive analysis of everything, and kind of present that to everyone and take feedback and really just review everything that we've done so far up to now. So I'll start with a few intro slides here. Maybe. Maybe not. There we go. All right, so the Spaceport team purpose, the reason that we exist in the Buckeye Space Launch Initiative is to compete in the 2023 Spaceport America Cup, which is a national rocketry competition hosted every single year by ESRA, which is the Experimental Sounding Rocketry Association. This year, it is taking place on June 19th to June 24th, so a little bit of the summer after the school year ends for us, but we'll still be heading out there to present BSLI and Ohio State's rocket. As the Spaceport team, we want to develop and present BSLI's most technically advanced rocket and kind of do the best we can to put forth our best engineering effort and kind of present our best work. And we also want to meet and engage with members from different areas of the rocketry community, right? So the Spaceport competition this year is going to be attended by over 150 teams from over 20 different countries, and we really want to have the opportunity to kind of meet with all these people and kind of share our thoughts and kind of learn from everyone else, and also just meet new people and make connections and all that good work. So for the goals and value this year, so obviously we compete in the Spaceport America Cup, but more specifically we compete in the 30K SRAD category, which entails a flight to 30,000 feet on a student research and designed SRAD solid rocket motor for us, which is kind of the highest tier of category at Spaceport of the 4 tiers. So that's great that we're kind of in the top tier of teams. As always, we want to try and prioritize the health and safety of every general member and lead at every meeting, really just to make sure that we're doing things safely and kind of in line with what people may see kind of out in the industry and things like that, and really try and give students experiences that will kind of help them to succeed and that they can kind of take forth into their workplace or wherever they just end up. As we do every year, we have to conform to ESRA's rules, the rules in the design, testing, and evaluation guide, as well as the rules and requirements that they give us every year, which change and that we kind of always have to make sure that we're conforming to, and which we really use to motivate a lot of our design and our requirements. Along with our motor being SRAD, student research and design, we also want to try and make our entire vehicle out of SRAD parts, so making our airframe and structures student research and design, as well as our avionics bays and our flight computers. Really, we want to do as much as we can to build everything ourselves and kind of be as involved as possible in every aspect of our rocket. And as always, we want to kind of supplement the experiences that students are getting in classrooms with kind of some more hands-on work, hopefully to kind of also make things more exciting, but like I said, to kind of teach more and kind of learn how to apply the skills and things like that we're all learning. And we also want to just make sure we're maintaining a rocketry community at Ohio State, kind of keep that thriving the way it is now. Right now, BSLI is kind of one of the only rocketry teams at Ohio State, but we're kind of making sure that we're kind of reaching out and expanding everywhere that we can. And that's been great, and we want to kind of keep maintaining that, especially for the Spaceport team. So as for the trajectory of this year, so coming off of last year, we placed 32nd overall in the Spaceport Cup, and we placed 4th in the 30K SRAD category, which wasn't the worst results, but we think we could do better. So this year, we really want to place a greater focus on kind of an in-depth analysis of our design decisions and simulations, really just to kind of make sure we're kind of doing the best that we can and we're not getting bogged down by unnecessary additions and things like that to the rocket. Really what that's meant this year is kind of trying to reduce the overall weight of everything, as well as trying to increase the capabilities of our current motor designs and things like that by increasing the impulse, which will hopefully help us reach a higher altitude and get to that 30K mark that we need to. We also want to continue maintaining a simple integration process. From what I've seen, it seems like the Spaceport Cup the Spaceport team at the Spaceport America competition has kind of one of the most streamlined integration processes from a lot of the other teams. So we want to make sure that we're kind of maintaining that lead and make sure that when we're putting things together, we're doing everything right, and we're kind of doing everything as smoothly as it can be done to kind of remove any issues. As of now, we are preparing for a April 1st test launch, so that's kind of the current deadline that we're all trying to meet. And then once we get there, we'll kind of hopefully move to kind of some finishing things, but as of now, that's where we are. So now I'm going to switch off to my Deputy Project Manager, Sarah Malaska, for kind of a breakdown of our team and a little bit more information.
All right. Hi, everyone. Like Zach said, my name is Sarah Malaska, and I am the Deputy Project Manager for this year. So here you can see a breakdown of our team. There's, of course, Zach, the Project Manager, and then myself, and then each of our 6 leads. You'll be hearing from all of them later on about their subsystems in detail. Here is a rocket overview. You can see the main structure of the rocket itself, as well as the subsystems on the interior of that. In addition, you can see our predicted apogee this year is around 37,000 feet. Our max velocity is expected to be just under Mach 2. Our max acceleration is about 511 feet per second squared, and our total mass with the motors is about 90 pounds, just under that. So how today will work is that each subteam will present 7 different categories. They'll go over their subteam purpose, their system requirements, their system breakdown, their testing plan, risks and mitigation methods, schedule for the year, and then we'll have 5 minutes for questions at the end. We encourage everybody to ask questions, anything that you're unsure about, something that you might want to hear more in depth, really anything that you're curious about or you have questions about. Our presentation order for today will be first structures, then aerodynamics, propulsion, avionics, recovery, and finally payload. In addition, you see some papers scattered about the room. That's the review item disposition. Would really appreciate if you guys could fill that out for us. Just good information for us to know and have written down. All right, so first up will be Ethan Butler, our structures lead.
All right. Hey everyone, like Sarah said, my name is Ethan Butler, and I'm this year's structures lead. And today we're just gonna be talking about kind of all of our different parts, our processes. And this year we did a lot of testing to prove how these parts are going to work in the rocket. So starting off with our sub-team purpose, our sub-team purpose is obviously to construct the body of a rocket that's going to be capable of surviving about a Mach 2 flight to 30,000 feet. We have to organize and complete the integration of other sub-teams' hardware. And this year I want to really focus on developing, fabricating, and testing new hardware so we can kind of increase our performance and any sort of engineering validity. So the system requirements of our sub-team, first, like I said, will be to house the hardware of all the other sub-teams, the ability to withstand that flight about Mach 2, as well as a smooth surface finish so that we can reduce any skin friction. That's a really big focus of ours. And then lastly, I want to successfully integrate our airframe within 3 hours. So if you're unfamiliar, at Spaceport you get a bonus for integrating on and launching on the first day. So that's obviously a big goal of ours. But I think we can really focus on kind of having a robust system that it's easy to integrate and it's intuitive. So the overview of our rocket you can see here on the screen. All the parts that are highlighted in red are things that the structures team works on. So starting from the left side, we have the fins. And so our team uses an aluminum fin can. And so that just is something we order and assemble in-house. And then moving on, we have the motor casing, which is something we order. That's also aluminum. And then one of the most important parts of our design actually is this transition piece. So that is a pretty integral part to our sub-minimum diameter design, transitioning from a 6-inch diameter to a 4-inch diameter motor tube. And so that's made out of fiberglass composite, which I will go over in more detail later. Then we move on to the coupler right here, and this is kind of the load-bearing aspect of the rocket. That's also aluminum, and that is in progress as well. Then we have the Integrated Systems Bay, or the ISB for short. This year it's fully student fabricated, so that's carbon fiber composite. And then moving on, we have some standard parts for the Spaceport team are body tube and nose cone, and those are also carbon fiber composite. And something new we're doing this year is utilizing the Nomex honeycomb core. So I'll start off with our first piece here, the nose cone. So the team decided to use a 2x2 twill weave carbon fiber this year. And I kind of thought of that because it's a more flexible material. And when you're making a nose cone, it can be difficult to kind of fit to the shape. So we used that this year. We're doing a Von Karman shape. That's from Aerodynamics. And then we also built a new mold you can see in the bottom left with the orange tooling face. And something I'm really happy about this year is I think the team got a new process for creating molds. I think we kind of refined that process, and we really made a really nice sturdy mold. One thing about the nose cone is it was a loose fit, which was a little on the strange side. Normally it won't fit and you need to sand it down. We think that's kind of due to maybe an out-of-dimension plug that didn't account for material thickness. So we're looking into that. But we are applying some filler to resolve any sort of fitting problems that we've had. So this is the recovery bulkhead. And so something new we're trying to do this year is what I call the 3H3 honeycomb fabrication. So that involves 3 layers of carbon fiber oriented at different angles, so 0, 45, and 0. That way we keep strengths on certain axes. And then a piece of honeycomb sandwiched in between. So you can kind of see it, you can kind of see it right here. This is, that's kind of the picture. I'll show better pictures later in the presentation, but that's the idea. It's kind of like a honeycomb sandwich per se. And so I will talk about our testing for that because we need to prove that. And basically the recovery bulkhead is going to house all of the recovery hardware, so the ejection canisters, eye bolts, U-bolts, things like that, and it facilitates the connection between our avionics signals and the recovery system. And then one more thing is something new that we are doing this year that we haven't done before is making this circular L bracket part you can see in the bottom right. And so basically this is going to act as a seal so that we can keep the ejection gases out of our ISB or the avionics bay as well. And so in the top right, you can see kind of a cross section how it's going to work is this circular ring will be mounted inside of the body tube. And then right underneath it, you can see what is going to be an O-ring. So we will put the L bracket in the tube, and then we will basically slide it down to compress the O-ring and keep the recovery charges and all those gases sealed up in the upper section. So now a pretty standard part for the Spaceport team is our body tube. So this is 6 layers of carbon fiber. Something we did new this year was actually attempt a new fabrication process. So in prior years, we had just used shrink tape to apply heat, and then that contracts so that we get a good shape on the mandrel. Something we want to do this year to maybe get a better surface finish was apply different materials. And so for those of you who are unfamiliar with carbon fiber wet layups, it basically involves infusing epoxy and hardener into carbon fiber fabric, and then you let it cure into a solid part. And so what we tried to do was add this material peel ply, which kind of just is this fabric that helps get a nice surface finish. And so we tried to do that, then breather, which is kind of a cotton absorption, I guess you could call it, material, and then peel ply again, and then shrink tape. So our thought was that it would give us a nice surface finish and soak out extra epoxy, so decreasing our weight. That didn't work so well. We ended up with a wrinkly body tube, so we kind of had to scrap that one, and we resorted back to what was always a reliable process, is just using shrink tape to really get that good body tube shape. So next is the Integrated Systems Bay, or the ISB for short. And so I'm excited about that this year because it's fully student fabricated. So some new aspects, like I talked about, we made honeycomb bulkheads that you can see at the top and the bottom. And we also compressively test those, which I'll talk about again later in the presentation. And we also created the carbon fiber rails. So that was a first for us. And that was cool because we got to kind of start from scratch with a new process, new part. And it turned out really well. They have a really nice surface finish on the inside. And kind of our thought with both the honeycomb and the carbon fiber rails was to reduce weight because we undershot our altitude goal last year, so we're trying to reduce our weight, and every pound helps. And so I actually calculated that we reduced about a pound off of last year's ISB, which, like I said, it doesn't sound like it would be that much, but when you're working with a 90-pound rocket, every pound is, it's a big difference. So next is our load-bearing coupler. So this is in progress right now. And so we're doing something new this year with the coupler, is we're adding this inner mandrel. And so basically I color-coded this here. So the green part is gonna be the part that will actually be our coupler, and the red part is gonna be taken off. So the red part is a mandrel so that when we go lay it on the lathe, we can kind of ensure that it's concentric. So there will be 4 screw holes in the base plate to put that piece on, but our finite element analysis was done with those there, so that is going to be of no issue to us. So that brings me to the FEA, or finite element analysis. And so this was, this was done with a factor of safety greater than 2 for both tests. And so the first one up here in the right, this is a compressive force of our motor. So basically it was run with supports at the top and the motor just compressing the coupler. And so you can see the max stress was kind of at the base plate where we find the welds, but this was well within, or well underneath the yield strength of the material. So that is of no concern to us. And then down here on the bottom, we have what's an exaggerated bending. So we applied a force of 1,000 pounds over on the right side. And again, you can see the max stress was near the base plate, but kind of on the smaller diameter. But once again, this was well below our yield strength, so we have no concerns in that. So next is the transition piece. And like I mentioned, this is a pretty important part of our sub-minimum diameter design. So this allows us to go from a 6-inch diameter body tube to a 4-inch diameter motor. And this year it's going to be longer. So we had to make a new mold. And that's kind of what this, little setup is. It might look a little janky, but so we're following the plug stacking procedures that we got from the Nolan lab. And that's where we're gonna be CNCing this. So basically, you stack this MDF and we're gonna make a negative mold. And so we're stacking this and then we will get that CNC'd and then we're gonna lay that part up in the next few weeks. So that brings me to the testing plan, and this is what I'm really excited to talk about because I think we did a lot of good testing this year, a lot of proof of concept. So we're gonna cover our compression testing, any recovery bulkhead testing, tensile testing, and then I'll briefly talk about our test integration and test flight. So our compression testing, I want to do this to prove that the honeycomb bulkhead could handle integration for the ISB because that shouldn't see too many structural loads. And we want to make sure that we could integrate that with no problem. So basically what we did was we used a torque wrench with this setup over here in the vice grip. And what we did was incrementally apply force, which I'll detail. And we used a washer to distribute that force. So we were using this equation here. The force is equal to the torque divided by the coefficient of friction times the diameter. So that brings us to our first result. And so I like to call this integration tight. That is in no way a scientific term, but it's kind of the first step. So that was our first test. And this is something that on launch day, this is how tight we're going to apply the torque. And so what you can see here in the first image on the left is there's the slightest bit of deformation. Tiny bit of compression, but then over here on the right, when you remove the washer, it almost rebounded, which was really cool to see. So that really proved to me I think we would be able to use it. So the next step was to obviously increase the force. So then we added 10 foot-pounds. And so you can see here that there is pretty significant deformation. But it did maintain its structure and all the connections. So this is in no way a catastrophic failure mode. And that calculated force was about 382 pounds. So that is something that I don't anticipate remotely coming close to on integration and launch day. So I think that's well within reason. And then we went up to 20 foot-pounds. And you can see over here, there's a crack right along the line. And obviously, there's significant deformation. And then you can see when we took the washer off, there was some grinding on the surface. And so ignore this picture for now. I'll explain that one in a second. But these two pictures on the right show that even with 20 foot-pounds, we get a crack, but that is in no way a catastrophic failure mode. And that was at a force of 764 pounds, which, again, I don't believe we should come anywhere remotely close to that on integration. So that kind of proved to me that the honeycomb was able to be used for our ISB bulkheads. Now this picture down here with the ripped off panel, so we did that on purpose because we wanted to look at the but that is pretty localized. Everything else maintained its structure really well. And we also didn't even have to worry about delamination. We actually had to cut this and rip it off ourselves. So even you can see in the picture on the top right, delamination was not really a problem. I think that came from our vacuum bagging. So I think we did a good job adhering that. So a little bit about the recovery bulkhead testing is first you have to address kind of what failure modes we need to look at. And so what my main concern would be is a full U-bolt, tear through and a threaded rod tear out as well. And so obviously those are pretty catastrophic to the flight success because the recovery system could just completely detach from the body tube. So what we're hoping to do is have a drop test. Hopefully Trent gets to do that sometime soon. And there I want to use the honeycomb and kind of analyze any results we get out of that. And then I will also be talking about our ejection tests that we completed. So our ejection testing results, the initial test that we did was really rushed. I think it was poorly integrated on my part as well. We were just trying to get some quick answers as to which bulkheads to make. But it kind of proved that you can't rush things because you need the detailed process and you need the actual results. So this was our setup for the first ejection test. So this on the left is an ejection canister, so that's where the black powder charges come out, and these are the threaded rods. This is kind of we had to makeshift a recovery bulkhead for this test. And so this is an eye bolt that we use to attach all the hardware. And then we have our avionics wire through here. And so the results from that one were not great. You can see in the upper right-hand corner, we had a little bit of tearing on the carbon fiber. And then right here in the bottom left, we had a complete tear out of our threaded rod. And we're not entirely sure on this one, on the threaded rods, because the recovery bulkhead actually got stuck in the body tube, so we kind of had to rip and jar at it. So we can't make any conclusive statement on the tear out with the threaded rods. But obviously, these two pictures didn't look promising at first, but it made me want to retest it with a better system. So our second test, we did thorough integration, and you can see the actual setup down here. If you look at the two in comparison, they're vastly different. We have an actual setup with washers, 2 eye bolts, U-bolt, and Trent, I'm sure, will explain all of this hardware later in the recovery section. But it was a lot more sophisticated, and we actually saw no damage to the bulkhead or the system as a whole. So that was really promising. So that proves kind of the ejection canister part of of the recovery bulkhead. Now we just need to prove the ability to withstand the impulse from when the parachute first deploys, and that's really my main concern. So that's what I'm hoping to get out of the drop test. So something new we did this year was tensile testing. And so this is still in progress at the CDME, but over here you can see the setup. We basically made tensile strips out of different layers of carbon fiber and just pulled them until they broke. And so our goal with that was to get some material characteristics of our carbon fiber so that we can start to have more accurate engineering models. And so over here on the right, this is 4-layer plain weave carbon fiber. So the early results look really good. It's really consistent with high strength brittle material. And it was really cool to see this because it's the first step in the direction of making engineering-based decisions on why we do certain things with our composites. So just a brief over the test integration and flight. So obviously one of the system requirements for structures is to integrate the rocket, integrate the airframe and the structural components. So we are gonna have a full practice integration before our test launch to make sure we get out any kinks in the system, kind of develop that system and make it robust. And then test flight, we'll have a full launch day integration. That's gonna be kind of a proof of our airframe and other components. And then we will investigate if there are any failures or any problems with our section. So that brings me to our risks to project success. So obviously with every project there are risks that put the success in jeopardy. So it's good to identify them and talk about how you can mitigate those. So one would be kind of time shortages and fabrication errors. So we ran into a few fabrication errors before. So that's just maybe a poor layup, out of tolerance part, a break or a crack or something along those lines. An integration failure as well. So that comes with the system. So if you have a poor integration system and you're trying to jam parts into the rocket and they end up breaking, that's never a good thing. Recovery bulkhead failure. So like I said before, looking at a U-bolt tear through, and that would be complete detachment from the body. And then test launch failures, so that could be in the form of any sort of crash landing or anything of that nature that would lead to us having to refabricate our parts. And so over here we will see the risk matrix and kind of how we're gonna go about mitigating those risks. So the time shortage and fabrication errors, that's really just sticking to a strict timeline. We have a good one on the structures team. I have a pretty detailed timeline myself. And so over here you can see that that's unlikely and that's a pretty minor risk because we can have more meetings and just make sure that we're efficient. Integration failures. So to mitigate that, we just have to ensure that we are detail oriented, we keep tight tolerances, we focus on the process, and we document our procedures well. And so again, that is unlikely and probably a minor risk to our success. And then the recovery bulkhead failure. So the way to mitigate that is to just test and prove that the system works. I do not want to fly anything until I've proved to myself that it can withstand both ejection charges and impulse from parachute. So that is unlikely, but that would be a major risk. I say it's unlikely because of our testing procedures, so we won't fly anything that we do not feel extremely confident in. And then lastly, it would be a test launch failure. So to do that, to mitigate that, we just need to ensure that we have efficient processes so that if there is a test launch failure, we can refabricate our parts quickly and have quality parts that we can fly. And so that is possible, and that would be a major risk to project success because then we're on a really tight schedule, time crunch for making our parts. And then this is kind of a broad overview of the coming schedule. So for the next few weeks, we're gonna be sanding and finishing off our nose cone, and then we'll also be making the transition mold. And then we're gonna transition into laying up the transition piece. So we'll sand and finish that down. And then something that I didn't really talk about, but we do have to do is lay up on our old test motor tube. So we have a new diameter on our motor this year, which is 4 inches. And last year we had a 98 millimeter. So our transition piece will have a lower diameter of 4 inches. So we need to add extra width to the test motor tube so that we can actually use it in our test launch. So that's something that we're going to be doing in the next few weeks. And then obviously we will be doing our test integration and test flight. And then as long as everything goes to plan, we're just going to paint and clean up all our parts, document our procedures, and then we'll head off to Spaceport in summer. So with that, I'm going to open it up to any questions. Yeah.
Is there any way you're like securing the L bracket or the bulkhead like down in position so we can use like compressive force on the opening?
Yeah, so the question for anyone online, I'll repeat the questions, was if we have a method of securing our L bracket. And I'll go back to that slide just to refresh what it actually is. So, right here. So this L bracket on the bottom right is going to be secured. We're going to be using structural epoxy to actually put that in the body tube, and that is going to have to be at a certain height so that when we do bring the tube over the whole ISP, it will compress it every time, and that's going to be pretty much epoxied in place. So that's how we'll secure it. Yeah.
Could you talk a little bit more about the honeycomb structure, like what the material is for that honeycomb, and how maybe you manufactured that, and how you're getting all those honeycombs to align correctly?
Yeah, so I will pull up, I guess this picture you can see it. So on the top is, for the question for the people online, was to talk about the orientation and kind of the setup of the honeycomb. So on the top you can see that this is our honeycomb bulkhead. And so setup-wise, basically you infuse your carbon fiber with epoxy and hardener, and then you put the piece of honeycomb, which is a Nomex core. So we actually have sheets of honeycomb. So that's something that we've ordered. And you basically lay up the sheet on top of the carbon fiber, and then you put more carbon fiber on top, and then you pull a vacuum. I think the vacuum was very important in keeping it from delaminating, because I think that has been the problem in the past, is that the panels of carbon fiber don't always adhere to the honeycomb. So the vacuum bag was really helpful in making sure.
And just to follow up on that structure.
Yeah.
So Nomex, what is that?
It's kind of like, it's like a paper-like material almost. It's kind of comparable to cardboard, kind of. So along those lines, it's really light, but it's really strong in compression. So, yeah.
You mentioned that you tried to do the manufacturing process for the body to be cotton, I believe. Now that you've experienced that, what would you do differently to try and stay process?
So I think the major problem with that process was just the sheer amount of material we tried putting on top of it underneath the shrink tape. So obviously when you're shrink taping, you apply heat and the tape contracts, and that's how you get your shape. And I think we really just had too much material underneath it, so it ended up wrinkling, and then those wrinkles just kind of showed themselves in the body tube. So I think I would just, if anything, if I was going to try it again, I would definitely just do less material. I think that order could work. It would just have to be a less sheer amount of material. Yeah.
You mentioned that when you were doing compression testing on the honeycomb, you got under, I think, 250 pounds of force, I think 750 if I recall.
Let's see. Yeah.
You mentioned that was far above what you anticipate on the actual launch. Do you have a number for what you're anticipating during the launch?
So I really wanted to do that actually, but I was kind of caught off guard when I was using the torque wrench. 10 foot-pounds is significantly more than I ever anticipated it was. So when you get it to a normal tightness, you were well below that. We had to go for quite some time before we even reached 5 or 10 foot-pounds on the torque wrench. So I wanted to quantify that number. I don't know if it's entirely necessary because it's such a low number. But I did really look into that, and I would like to have some sort of quantifiable, I guess, metric for launch day that you kind of just check off. So that's something I guess I could try to figure out a different way to do it, maybe, a different number to check off, but definitely looked into that, yeah. Yeah. No, it was just the dry zoom. Okay. No, I actually haven't looked into that, but I really should, because I didn't even think about the loss of friction on the torque. So it's just like, this was three layers of carbon fiber on the bottom and top. Mm-hmm. So we could also look into doing a different amount of layers, I guess, to make it stronger as well. That'd definitely be something to look at. Cool, yeah.
Everybody hit pretty much everything I sent out. I know it was brought up last year about torque specifications and all this stuff.
Mm-hmm. Yeah, so that's something, I really want to do that. I guess I kind of need a little bit of guidance almost on that, because I could set up my own standards. At the same time, though, I would need, one of our members actually brought in a torque wrench. That's kind of how we used it. So I guess I could purchase one. Last year, we tried using one. I don't know if you remember it all, but we used that digital one. That really didn't work so hot. But I would like to do that. I got to look into if there's like an industry standard, I guess, for how tight you keep things. I know on certain things there's torque levels, like a lawnmower blade, for example, or something like that. But I would like to get that down because I think that's like moving into engineering type qualities. That's kind of industry standard. You actually need a number to get to and check off. Yeah. Yeah.
Doesn't have to be exact, but it's a good idea.
Yeah.
The last thing, and nobody else brought this up, is that O-ring seal
Yeah.
on the inside.
Mm-hmm.
That's a nightmare every single year you guys have tried to do that
Yeah.
on integration, trying to get that inside.
Mm-hmm. So I think we had a different thought this year, and it was kind of to drill holes in the side of the body tube so that we can put our epoxy in and not have to reach in there and try and like look in like that. Because last year I do remember that was a really big pain. I think that this system will work well as long as we do get that position right, but that is always tricky because it's got to be level too. But I think we're going to go with a different approach, trying to drill the holes and kind of infuse the epoxy that way.
I just think you gotta test that before, the night before test launch, is the one that you gotta get together.
Yeah, yeah, definitely. Mhm. Yeah, it's just tricky getting that right spot where you get the compression. Yeah.
You were talking about regional, in the event of like a one failure. If you give us like an approximate percentage on like what percentage of your time, has so far been spent on like R&D and preliminary design of molds as opposed to like actual construction? So like, are we looking at like a, an extra 20% of your time currently, or like 50% of what we're doing?
Yeah, so creating the molds actually is quite a process. So if we have the molds, creating the part is pretty quick. We can make pretty much any part in one meeting. But I'd say about in the past, like this semester, we've probably spent 50 to 60% of our time on molds. So it's definitely a big time consumption. And that's what we're about to make a new transition mold too. So in the event that that happens, once we have the molds, we should be able to make the parts pretty quickly. So I think we should be all right with that. Yeah. Yeah, so we use an ASTM. Do you remember the number off the top of your head? 3039. And so one thing we probably should have considered, honestly, if we should have done a better job, is maybe doing the dog bones instead of just the flat strips, because you get kind of a buildup of stress on the grips, and that's kind of led to maybe occasionally a weird break. So it's definitely like it's something to consider to like find an exact standard, I guess. I'm not entirely sure on how to pick the standards. I don't have too much experience in that whole realm, but I think that's definitely something we need to focus on if we do it more extensively. Any online questions or no? All right, cool. Thank you guys.
The thing's not working anymore. Oh, there we go. All right, guys. Hi, my name is Sawyer Haman, and I am our Aerodynamics lead this year. And so our sub-team's primary purpose is to gain insight as to how the rocket performs in terms of drag and stability. We want to assist with developing an accurate prediction of the rocket's apogee, and then also continually throughout the whole year enhance our team members' understanding of fluid dynamics and how to use CFD. So our team's requirements, we want to analyze drag and stability of the rocket, of all the aerodynamic components, and then based off of those results, we want to recommend geometry changes to optimize flight in terms of drag and stability. And then finally, we want to acquire accurate drag coefficients through all flight regimes and try to accurately assist in predicting the rocket's apogee. So a big thing we've been working on this year is analyzing our rocket's nose cone. As Ethan said earlier, previously through all our years, we've been using the LD Hack von Karman design. It's a shape derived to reduce drag. Through some rocket geometry literature, we found that a power series nose cone could produce comparable to lower drag results. And so pretty much we wanted to verify that we were using the correct or most optimal nose cone design to reduce drag. And the primary difference between the two designs is the power series nose cone has a more blunted tip than the von Karman's very pointy tip. And then we've just got pretty much the equations on how the shapes for each design is derived and sort of just what each of those variables in these equations are. And here's just a quick little chart from some literature we pulled up comparing the drag performance of each of the two designs we're looking at all range of Mach numbers. The two, they perform quite similarly. Primarily, we wanted to see how the power series nose cone performs in the higher transonic region as compared to our current design of the von Karman nose cone. So how we did most of our testing of this is using ANSYS Fluent 2D CFD simulations. Pretty much, we have a rectangular computational domain and a little cutout of the rocket at the bottom. We just simulate flow over that in the domain. And then we used two different geometries, one with each different nose cone, and then compared the results. Primarily what we used is a K epsilon turbulence model with scalable wall functions, pretty much just a set of values and equations used to simulate turbulence. We aimed for a Y plus of 40. That's pretty much just determined by which turbulence model we want to use. Pressure-based solver, we used quadrilateral dominant mesh, so pretty much just these four-sided kind of square cells, and characteristic length of about 115 inches, which was, at the time, the length of our rocket. And so these are kind of the results we were looking at while we were doing our tests. This is sort of just a pressure contour at about Mach 1.5 between the two designs. Yeah, so in here you can kind of see where the different shocks in our rocket develop, so that's pretty cool. Results from our nose cone testing. We've got a table on the right there of the drag coefficients between the two versus Mach number on our x-axis. The results were very similar, and we decided that they weren't conclusive or drastic enough to warrant a geometry change, sort of verifying that we were using the nose cone design that we wanted to stick with. And then here's just sort of a similar graph of drag versus time of the launch. Very similar results between the two different designs. Transition piece, we worked on this some too. Reevaluating data gathered last year. We determined that we wanted to make our transition piece 20 inches long rather than 15, which it was before. We sort of gathered drag and weight increases as we increased the length of transition piece, and found it would be optimal to make it 20 inches long. Anything after that would be sort of arbitrary. Let's see. What we're working on now a lot is the implementation of a boat tail on our rocket. We want to analyze the base drag effects of implementing one or not having one. And currently, the results we are gathering seem pretty consistent with literature that we've been comparing our results to, and that a boat tail will probably reduce our base drag. 3D simulations, which is something we've been working on lately as well, which has been taking a lot of time and trial and error. Similar to our 2D simulations, we use symmetry to sort of speed up our simulations. We just do quarter body 3D simulations, simulate the flow sort of over this quarter body rocket boundary. And the advantage of these 3D simulations is that we can implement our fins, which is we can't really do in our 2D simulations. And with this, we can gather accurate drag results for the entire rocket, which will help a lot in predicting our apogee, and rather than just geometry changes. Testing plan, pretty much what we've been doing all year and what we will continue to do is utilize literature results to verify the rationality of our computational results. Been using adaptive mesh refinement studies to verify the accuracy of our meshes and simulations. We want to compare the computational drag results and altitude predictions to our test launch data, which we're going to have in early April. And then later on, we can additionally verify the results with hand calculations. Primary risks to our project success: errors from meshing inaccuracies. Our computational results can be a little bit off if we have any meshing errors or weird cells around our rocket. Over and underestimation of drag. If we overestimate our drag, this could lead to a heavier rocket. If we underestimate our drag, this could lead to a failure during flight, a structural failure. An incorrect estimation could lead to a poor calculation of our rocket's apogee and inappropriate geometry changes. Here's our risk matrix. So we've got errors from meshing inaccuracies as A here. It's possible. It's difficult to get a perfect mesh, but the effect of that is not great. Pretty much what we can do to mitigate this risk is verify our mesh with that Y plus value and our adaptive mesh refinement studies. And then additionally, our other risk, we've got the over and underestimation of drag. It would probably be much less likely, but more significant to our flight success. What we've been doing to mitigate this is our literature consultation, just all those other things I said, hand calculations. Want to do 3D simulations to sort of grasp a better drag analysis of the full rocket and compare those results to open rocket results. Schedule for the whole year, pretty much the whole year we want to work on teaching our members CFD and particularly ANSYS Fluent. We're pretty much done with our nose cone analysis. We finished that up around the end of last semester, along with our transition piece analysis earlier on this semester too. What we're working on now is, like I said, our 3D simulations. We want to get an accurate reading for our actual drag values for all flight regimes. And then using those, we can begin the assistance of developing an accurate altitude calculation. After our test flight in April, we can use our test flight data to work on verifying our models and calculations. And then after that, we can prepare our results for competition. Okay. That's all I've got. I'm open up for questioning. Yeah. Right. Yeah, so let's see. It's sort of shown in this little diagram here. The boat tail is sort of just a little angled conical section that you put at the bottom of the rocket, pretty much to, at an angle, reduce the diameter of the end of the rocket and pretty much change how much the air has to drop off and reduce sort of the pressure drag there. Yeah. Yeah.
So to follow on to that question, that rocket in the diagram is being full diameter body. Since we're using a sub minimum, would that boat tail be at the end of the motor tube?
Yeah, so the question was, since we're using a sub-minimum diameter design, where would the boat tail go if we're using one? Yeah, it still would be at the bottom of the motor tube, yeah. Yeah.
So how does that analysis differ from analysis of the transition piece? Because both kind of that like narrowing of the power.
It's pretty similar. That is also sort of what the purpose of the transition piece was, is to sort of reduce that diameter going down the rocket. But the primary difference is just with the boat tail, there's the drop off with there's no body after that. And so that's sort of where the base drag analysis comes in. Whereas the transition piece, we have the motor tube after that, yeah. Yeah. Okay. Yeah. Just a general reduction in total drag and drag coefficient of the entire rocket. Yeah. Both. Yeah. Yeah, go ahead. 38. Oh, right, yeah. That's just like an ambient pressure from open rocket simulation. Yeah. Yes, I'm pretty sure it was. Yeah, yeah. Okay. Okay. before. Yeah. Yeah. Probably what it would be is using a test flight open rocket simulation, and then gathering our own drag result, or using ANSYS Fluent, gather drag results from that, and then using this other calculator pretty much to compare how close, it was like we implement those drag values into open rocket simulation with a different plugin, and then compare that to the actual sort of just like acceleration and then altitude of the rocket during the test flight. Yeah. Yeah. Okay.
Have you, this is a serious consideration for adding to the rocket this year. Have you been engaged in discussions with structure subsystems that also make this be attached to the base rocket? From what I recall, with that motor tube, you have to have the thing to be a thin can, so that this is the added drag that whatever fastener is that you would need in order to mount something down on the bottom of the rocket.
I think pretty sure it screws into the bottom of the motor tube, right? Isn't that all it is? Yeah. So that's it, yeah. All right, any online questions? Okay, sweet. All right, I will pass it on to Noah then, our propulsion lead. Oh, sorry. One more question. Yeah.
So that, the boat tail is being considered for this year?
Yes, yeah. So it is, yeah.
All right. My name's Noah. I'm the propulsion lead. So the purpose of our project is to research, design, build, and test the solid rocket motor. We also just, of course, always want to give students hands-on experience with rocket propulsion and rocket propulsion test systems. So the requirements for our system, we want to build this motor so that it can send our rocket up to 30,000 feet. We also want to design the motor for the test flight. It's obviously going to be a different motor since we only want to go to 5,000 feet. That will be commercially purchased. So we will just run simulations to determine the amount of thrust required or given the weight of our rocket to get it to 5,000 feet. We always want to research methods to maximize the motor performance while also minimizing the weight of the motor. And as always, we want to maintain safe testing and launching procedures. So these are the structural components of our rocket. We have the motor case. It's an aluminum tube. This year, it is 66 inches long and 4 inches in diameter. Then we have the forward closure, which is going to be threaded this year. It's a threaded aluminum structure that seals the forward end of the case. It's also used to attach the motor to the rest of the rocket. And we have our O-rings and our retaining rings. These are just used for retainment purposes, so for the closures, and the O-rings are just used to seal the gases inside the motor. These are our propulsion components. We've changed the nozzle dimensions this year. They change every time that we change the motor. So our nozzles are made from graphite, and they're used to accelerate the flow and control the flow to deliver thrust to the rocket. The throat diameter of our nozzle this year is 1.4 inches. The exit diameter is 3.44 inches, which gives us an expansion ratio, which is the ratio of the area of the exit to the area of the throat, of 6.08. And our propellant is in the form of solid grains. Our propellant is ammonium perchlorate composite propellant. These grains, as you can see, have a hole in the middle. It's a cylindrical core dug out from the grain That is where it is ignited, and that's what acts as our combustion chamber. Here you get a good view of our overall system assembly. Here's sort of a translucent, transparent view of the motor tube and the liner. This is without the liner, sorry. Here it is all together. This is what it'll look like. You can see here, that's the boat tail that Sawyer was talking about. And down here you can see that is, so the nozzle here is put into the nozzle carrier, which is just an aluminum structure that's threaded, that'll be screwed into the overall motor tube. Then this boat tail is connected to that via screws, I believe. We don't actually have this hardware yet, so we aren't completely sure. Actually, the person that we are purchasing it from and designing the hardware with, he hasn't even gotten the hardware to build the hardware that we need, so the exact dimensions of and how they are going to be manufactured are currently up in the air. But we have a good general idea, which is how these models were created. And then we have the forward closure, and this is all sealed with a few O-rings. Here's our propellant stack. This is a 6-grain stack. Each grain is 10 inches long, so that's 60 inches of propellant. So we'll get into the overall scope of our project this year. We wanted to rework the motor formula composition and also the structure of the actual motor to deliver more thrust to the rocket. Last year we had 6% aluminum and 2% magnesium. These are the solid metal fuels. They're in the form of a powder, and you mix them into your propellant with your oxidizer and a binder. This year we wanted to get rid of that magnesium, as magnesium is a little more volatile than aluminum. It burns hotter. So removing this magnesium and replacing it with 2% more aluminum, giving a total of 8% aluminum, that will reduce the burn temperature and the max pressure of the rocket, or of the motor, and it'll just make the burn a little bit more predictable. We have also, as I mentioned earlier, we have a 4-inch case now. This is an increase from the 98 millimeters that we've always used. It's an increase of about 3.6 millimeters. So it's not that big, but when you're increasing diameter for a 60-inch propellant stack, it definitely adds up. And like I just mentioned, we have a 60 inches of propellant. We usually have 48. So our overall motor case is 66 inches long, and that extra 6 inches is just from space for the nozzle at the end of the motor. This year, since we are taking a more student-led design approach to the motor structure, spaceport requirements say that we must test the motor case, like a pressure test, up to 1.5 times the operating pressure of the motor. So this operating pressure of the motor will just be the pressure that we see in the simulations before we do static firing. So we're going to test this hydrostatically, and I'll get into that. I think it's on the next slide. We also want to do full-scale static fire tests of all of our flight motors. And we want to use the results from these full-scale static fire tests to actually reconfigure the grain layout. So what I mean by that is we have 60 inches of propellant, 3.6 something inch diameter grains. That's a lot of propellant, and it's likely a lot more than we need. So what we can do, we have a few options. We can substitute a grain or part of a grain with just an aluminum slug, and we might hollow out that aluminum slug just to make it a little lighter. Or we can substitute a certain amount of the propellant with something called a smoke grain, which is just like a regular propellant grain, except it doesn't contribute to the thrust. It just burns and smoke comes out, and it might actually make our rocket easier to track throughout the powered phase of our flight. So yeah, here's our hydrostatic testing plan, we're still working out the kinks here. This is something that we realized we needed to do not too long ago. So we're still putting together a procedure. We still need to put together safety procedures because we plan on testing up to 1100 PSI, which is no joke. But we're gonna need to machine 2 new closures for our motor case because the ones that we have, like the forward closure, that's not gonna work with it doesn't allow us to use the proper steel fittings that we need to connect a hose to a pressure tank. And obviously we can't use the nozzle. So one closure will be completely sealed. It's basically gonna be a threaded block of aluminum. And one closure will have a threaded hole sized for a steel tube fitting. So the procedure starts, we fill the motor case to approximately 95% with water. And the reason we're using water instead of just pumping the whole thing full of air is because water is incompressible. So, or at least very, very, very slightly compressible. So instead of having to pump a ton of air or nitrogen or argon into the entire tube, you only have 5% of that open space that you have to pressurize, and the water will do the rest of the work. So once we fill it with water, we're gonna connect high pressure hosing to the motor case and then to a nitrogen cylinder. This is in collaboration with the liquids team. They have a lot of experience doing these types of pressure tests, so we will be relying on their expertise. They also have the nitrogen cylinder, and they have a lot of the equipment that we'll be using. We want to manually regulate the pressure increase to the desired 1100 PSI. It's something we can't really do remotely, so we will have to have somebody on the regulator adjusting that manually. Then from a distance, using a remote data acquisition system, we're going to acquire the pressure data, and I believe we have to submit that data to Spaceport. And then we're going to slowly unload the pressure from the motor case and then drain the water and clean the case interior, and it'll be ready for testing. So these are our performance projections. This is for our 60-inch propellant stack. So this is a full-size motor, fully filled with propellant. So this is a very powerful motor here, and which is why I talked about substituting part of the grain with an aluminum slug or a smoke grain. So this gives us a total impulse of around 30,000 Newton seconds, which is a 75% O motor. The average thrust is around 5,200 newtons, or almost 1,200 pounds. The burn time is 5.85 seconds, and the max pressure is around 700 PSI. You can see here, this is the profile of the thrust curve and the pressure curve. So it's quite a progressive burn, but we still plan on spending some time trying to even out this and make it a little bit more flat throughout the flight. But it's not a concern. Even if we went with this, we're really not concerned about that much of a progressive curve. So this is the flight simulation from the 60-inch propellant stack. We are going to 51,000 feet here, so obviously we do not want to use this motor case full of 60 inches of propellant. We get a max velocity of 2,700 feet per second, which is almost Mach 2.5. Max acceleration of 746 feet per second squared. And the total mass with this motor fully filled with propellant of the rocket is 1,333 ounces, or 83 pounds. So to try and fix this issue, we have run more simulations with less propellant. So this is a 50-inch propellant stack. So we've completely removed an entire grain of propellant here. Still the BSLI white formula. So this total impulse has gone down to around 25,000 Newton seconds and is now a 63% O motor. Compare that to the 75% with the full stack. The average thrust here has gone down to about 978 pounds. The burn time, it has gone down to 5.92 seconds, and the max pressure is now at 672 psi. Still have that progressive thrust curve, but again, not really worried about it. This is the simulation from that 50-inch propellant stack. So we're still going well above 30,000 feet here, but the thing about open rocket is that it isn't able to take into account the large increase in drag that you get when you transition from subsonic flight to supersonic flight. So in theory and in our experience, we always tend to shoot a few thousand feet below this predicted apogee. It's usually around 3,000 or 4,000 feet, so we are going to spend some time and try and get this lower and create a good solid motor design that'll take us to around 33,000, 34,000 feet. This max velocity has now gone down from 2.5 to 1.9, or Mach 2.5 to 1.9. The max acceleration has gone down to 511 feet per second squared. Oh, I forgot to mention, this is with the aluminum slug. We've added a mass that is around the mass that we would have with a 10-inch aluminum slug. So the overall mass of the rocket with the motors has gone up from around 83 pounds to almost 89 pounds. So the risks that we could face here, obviously the biggest one is an explosion of the motor, a CATO, catastrophic failure, or an RUD, which is a rapid unscheduled disassembly of the motor. This is due to the overpressurization of the motor case, or it could have something to do with if the motor case was not properly manufactured. Maybe there were cracks that the manufacturer didn't catch that could make it more susceptible to exploding at a lower pressure. Our rear closure could fail, so that's our sort of assembly with the nozzle and the nozzle container and then the tail cone, or the boat tail. This could be due to more manufacturing imperfections in the nozzle or another piece of that hardware, or say like the threads on the tail cone with the nozzle retainer, those could fail due to overpressurization. We could also have an ignition failure. One way this can happen is if we have a chuffed ignition, which is essentially when you go to ignite the motor, you start the burn, but the pressure isn't able to build up fast enough in the motor for the burn to continue and spread throughout the rest of the propellant. So it kind of just like spits and sputters and doesn't actually go anywhere, and it won't ignite. Could also just be due to poor igniter placement in the flight or in a static test. Also, the insufficient / excess thrust for the 30K goal, that's almost a given. We're likely not going to hit 30,000 feet on the dot. So, like give or take a few thousand feet. So this could happen because the motor spits out a piece of the grain, like the propellant grain, or it could spit out a piece of the liner, the motor liner. That has actually happened in multiple static tests that I've been a part of, and it's one of the leading theories of why we undershot the altitude goal last year. Could also just be due to discrepancies between simulations and static fire tests. Like I said, the open rocket simulations aren't completely accurate. So it's really hard to know for sure, but still doing our best. Here's our risk matrix. So the motor explosion is definitely severe and very rare, but that would be a catastrophic failure of our rocket, or at least the motor. So one way we're going to mitigate this is performing that hydrostatic test to, just so that we know we're not going to overpressurize the motor. And obviously we static fire each motor that we plan on flying. We're going to static fire that sort of propellant layout. Rear closure failure, that would be a major impact because it could also affect the structural integrity of the actual case that holds it. All we can really do about that, other than performing this hydrostatic test again so that we know we're not going to overpressurize the case, is just to do very close inspection of all the hardware that we receive. That's always a good engineering practice anyway. We could have ignition failure. We're just going to practice with our igniter placements, and the motor should get up to pressure based on our design using the simulations. So we're going to make sure our simulations are sound and get a lot of practice with igniter placement in static fire tests. And then the insufficient excess thrust. Remember I said that a piece of the liner could spit out, and that has actually happened to us before. We've always used cardboard liners, and the liners aren't meant to burn up while you are firing the motor. But cardboard, it has some thermal resistance, but we plan on using phenolic motor liners instead of cardboard. And phenolic has an R value of R5, I believe. And for cardboard, I think it's R3 or R4. And what an R value is, it's a measure of the thermal resistance of a material. So the phenolic liners are going to be more thermally resistant than cardboard. So we don't expect to have any more issues with a piece of the liner spitting out of the nozzle, which would lower our maximum altitude. Here's our schedule. It's a pretty tight schedule right now. Considering we don't have our hardware yet, we have a lot to do once we do get that hardware. And it's going to be in a very short period of time. So we plan on receiving the motor hardware sometime in these first 2 weeks of March. And after that, we will immediately go to the hydrostatic pressure test. So we will spend time in these 2 weeks, as we don't have the hardware, we will spend time planning out how to actually perform and go about doing that hydrostatic pressure test. Immediately after we're done with the hydrostatic pressure test, we're going to travel to Dayton to mix propellant. And then immediately after that, we will do our first full-scale static fire test. After the static fire test, or the first static fire test, we will then adjust the grain layout using simulations, and then we will head to Dayton again to mix a new motor. And after that, we will have our second full-scale static fire test. And if that isn't enough testing for our purposes, say we aren't able to nail this second motor, we do plan on scheduling further tests. It will just likely have to be sometime in the summer before competition. Any questions? Yeah.
Are there any alternatives on the market for simulation software that does do that or does it better? Or are there any sort of mitigation plans in place to work on getting more accurate simulations so you don't have to do this kind of estimation around getting it picked up properly?
Right. So the question was, do we have any plans on sort of trying to either find a new software other than OpenRocket that is able to account for the transition from subsonic to supersonic, or if we just had any plan in general on sort of refining how we actually deal with our results from OpenRocket, or how we are going to account for that. And the truth is, I'm sure there are. I'm not aware of any other softwares. OpenRocket is free, so any student can get on OpenRocket and design a little motor and design a rocket and simulate it. So I think that's one of the big reasons why we use it. But I'm truly not aware of any, unless we wanted to use something like ANSYS somehow, if we were to create a model for ANSYS of our entire rocket, but I'm not sure how that would work. But yes, sorry, I'm not very familiar with that. As for sort of refining how we deal with our results from OpenRocket, there aren't any plans to change how we look at those results. It's kind of just based on past experience. So we've seen these rockets go 3,000 to 4,000 feet less than the open rocket prediction. So that's kind of all we have right now to go off of. But that is a good suggestion, and I'll definitely look into that. Yeah. With a lot of elbow grease. We have brushes, we take literal toothbrushes and just sort of scrub it out so it can be reused. We have to remove any charred bits that remain. We'll have to get a new nozzle, but other than that, we just sort of wipe it down. Yeah. Uh-huh. Mhm.
With using threads for your forward closure and your mouth retainer, do you have any concerns about the difference in material or difference in construction of the bulkheads, changing the way your plugs might be validated against that hydro-proof testing?
I wouldn't say we're very concerned. The motor case will have internal threads, so we're going to have to create the same thread pattern. The same sort of thread pattern will be on the forward closure that we plan on using for our flight and the closures that we plan on machining. I'm not aware of any differences, I guess. I think it's aluminum 6061. Yeah. Yes, yeah.
Do you have any concerns on that with the thermal environment? I imagine water is going to be, ambient 60 degrees Fahrenheit. Do you have any concerns, thermal concerns with the changing performance of the material, especially near the rear end where you have an outlook area during
In the performance of, oh, I see, like, okay. So the question is, do I have any concerns about the difference between how the motor case will perform under pressure at whatever the temperature of the water is, which will be much less than the actual temperature when it's burning? I didn't really think about that. Now that you say that, that would be something that I'm not actually sure how that would work and how the increase in temperature affects the like structural integrity of the aluminum, or to what extent we can increase that temperature before it becomes a problem. But that's definitely something I'm going to look into, so thank you. No, go ahead. That's,
static testing in the past, we've had historical data quality issues from sensors that have experienced a variety of past conditions, either in test or in storage. And that could also be a contributor of the issues we saw last year with flight performance not lining up with predicted. Do you have any plans for new instrumentation, a calibration plan for your instrumentation, or something more?
I don't personally. I also am not really involved too much in the instrumentation. That's more of avionics. So, oh, for static testing. Yeah, we are going to be purchasing a new load cell. Other than that, we will still be using the same pressure transducer. It'll be the same dimensions. Yeah, that's probably it. I think we have had issues with the pressure transducer, but I think we have one that is working well now. Yeah, they will certainly be calibrated before we use them. Yeah.
One last question, and I'll let you go, I guess. So you're increasing the length from 66 inches to 66 inches from 44, and it's 40 inches to come up to 60. Does that sound right?
Yes.
Actually, let me see some parts. So first of all, you were talking about using that aluminum slug up to the top to kind of decrease that effective, I guess,
Yep.
Do you have any concerns with that aluminum slug staying in place, like during the motor test, which needs nominal acceleration? Do you have any specific ways you're planning on attacking that, or is it just going to be floating?
It certainly wouldn't be floating, but we would probably use some sort of adhesive to secure that aluminum slug into the motor so that it doesn't move after the propellant, downstream has all been burned up.
And also come up real quick, so we're increasing the length of the core. Have you guys done anything to increase the core stepping or the core diameter to prevent the waste of burning through the mass flux?
Yeah, we are, the last 2 grains of those 6 are stepped. So the question was, are we going to, there's something called stepping your grains, which means increasing the core diameters of the lower grains toward the nozzle. And this reduces something called erosive burning, which can, I won't get into the theory, but it can cause issues and increase your burning surface, decrease your burn time, increase your max pressure. It can chip off pieces of the grain, so it's really not good. Yeah, the bottom 2 grains are stepped, so the first 4 grains are all constant core diameter, and then it increases to, I want to say, it varies between the 2 different motors, whether it's this full 60-inch stack or if it's the 50-inch stack. But I think we go from 1.3 to 1.425 and then to 1.5. It's something around there, but yeah, we are. Yeah. Yep. Yeah.
So I guess I kind of noticed a discrepancy. So structures and aerodynamics talk a lot about reducing weight. They talk about looking at like the benefit of weight reducing pieces opposed to increased length. Structures are talking about the weight for the ISP. But I noticed that you didn't seem too concerned about adding about 5 pounds with that aluminum slug. So I guess the question is, do you have a target weight in mind, and are you, or target mass in mind, are you communicating that to the teams, or is it kind of just a little bit of a disconnect in terms of weight target for the system?
It's not so much a disconnect. It's more of we don't have a whole lot of options for ways to replace propellant in the motor. So an aluminum slug, we could reduce the weight of that slug by hollowing it out, say, like drilling a core up to where it connects to the grains and then leave that surface completely solid where it connects to the grains. That was one of the reasons we thought about doing a smoke grain. And I personally would like to go with a smoke grain, is because it would be less weight. Yeah, you saw that it was an added 5 pounds for that aluminum slug. So, yeah, that's sort of where we're at with that right now. Any other questions? Anything online? Nope. All right. Next up, we'll have Peter Hall. The avionics lead.
All right, hey everyone, I'm Peter Hall, I'm the avionics lead, and I'll be going over our electrical and software systems this year. So the primary purpose of our subteam is to develop the electrical and software systems we need, primarily to ensure successful recovery, that's the biggest goal, but then also record additional data, transmit that data, and then track the rocket. Sort of a secondary goal we have this year is to expand the opportunities that BSLI offers for electrical engineering and computer science students. By sort of having new projects and working on things that are maybe a little bit outside the scope of the strict rules, but provide opportunities to learn and gain experience. So a couple main system requirements. The first one is to fire the energetics to eject the nose cone and deploy the drogue parachute roughly at apogee. And then secondly, we want to fire the energetics to deploy the main parachute at around 1,500 feet. So again, those are like the 2 biggest, most critical goals. But some other ones, this year working on an entirely SRAD flight computer as the primary altimeter. So that's a pretty big project. I'll get more into that later. Also live telemetry transmitted via an SRAD communication protocol and ground control software, which we have developed this year. We also, for the purposes of safety, have remote arming, so we can arm the rocket and the energetics for recovery from a distance, just to make sure we're all safe and far away in case anything goes wrong. We're also looking to collect flight video this year, and all of our systems on the rocket are going to fit into a 1.5U CubeSat form factor. And just as we're working through all these requirements and making engineering decisions, there's always two things in our mind, which are redundancy and reliability. Both of those are very important to our system to make sure everything goes nominally. Just to give a general overview of the system on board the rocket, we have everything contained within a 1.5U CubeSat. We call this the Avionics bay. And within that, we have a modular setup, so there's 3 main printed circuit boards, or PCBs, which are connected to a larger PCB called the backplane. And the backplane handles interboard communication and power distribution for various subsystems. The 3 main boards inside the Avionics bay, so starting on the left here, a little bit difficult to see, but we have the arming board. So this board, attached to it is our commercial flight computer, which is the Altus Metrum Telemetrum. In the middle, we have our telemetry board here, so that contains our radio modem for our RF link. We have our SRAD flight computer on the right, which again, I'll talk about more later. And then in the event that our SRAD flight computer cannot be validated before the time of launch, we have an additional slot here where we can put in a second arming board with a second commercial flight computer. And so all this system on board the rocket is controlled via an SRAD ground control software. So here's a schematic of sorts of some of the critical electrical components on the rocket. I'll start down here. So we have a ground control software connected to a radio modem on the ground, and we have a radio frequency link at about 900 megahertz between the ground and the rocket. So on board the rocket, we have a radio as well, and some antennas in the transition piece. This communicates to the flight computer, and the flight computer handles a couple of things. So it interfaces with other systems on the rocket via the CAN bus communication protocol. I'll describe that more in a second. So this flight computer, again, it acts as our primary, fires the primary energetics. So we have an arming system, we have our backup arming, I'll talk about that, and then our energetics here. It also communicates across over to the arming board, which will arm the commercial flight computer. And then we do have some peripheral components. So we have a bit extra battery, we have an Altus Metrum Tele GPS, and some other components that aren't strictly critical for the recovery. So to discuss the backplane, so this is a large PCB which all of our other boards are connected to. It does a couple things, like I mentioned. It regulates the battery voltage down to +5 and 3.3 volt supplies for different electrical components that require those. And then it handles communication between the other PCBs. So the boards plug into these slots here. There's 4 slots, and they communicate via a controller area network, otherwise known as a CAN bus. It's a very robust communication standard used throughout the automotive industry, also in the aerospace industry to a lesser extent. Some advantages of it, one of them is that it is largely decentralized. So for example, if one of these boards were to come loose or brown out for whatever reason, the other board should still be able to maintain communication with each other. Additionally, it's semi-asynchronous, so it's not fully asynchronous, but we can send data or send packets with an asynchronous clock signal, so it allows communication between different systems to be a little bit quicker and more optimized than otherwise possible. We also have a USB-C port up here for a number of purposes. For charging the battery, we can just plug in there. We can also use it to connect to the custom flight computer for programming or just retrieving data. So to discuss, just going from left to right within the Avionics bay, we have our arming board, which is connected to our commercial flight computer. So nominally, this is armed remotely via our radio connections. So in our software, we'll send a signal to arm the rocket. The flight computer will process that. It will send another signal to here, which will basically connect the commercial flight computer to power, at which point it will be armed. If for whatever reason this radio link fails, there is a physical button inside the rocket, so we'll drill a hole in the body tube, and you can reach in there and press that button, And if you hold it down for about 2.5 seconds, it will toggle the state of arming. So whether we need to arm it or disarm it, either one can be achieved that way. A change we made from last year is on the arming boards last year, they used magnetic mechanical relays to arm the systems. And this was a risk for two reasons. First of all, vibrations with a mechanical switch are always liable to accidentally come undone. But also payload, as Adam will discuss, has some magnets this year, and we don't want any risk of our system accidentally arming or disarming at an unintended point. So we just switched to a solid-state transistor or a MOSFET to address that. Like I mentioned before, the commercial off-the-shelf flight computer we'll be using is the Altus Metrum Telemetrum. We've used this in years past. It's proven to be very reliable, and it's just a very popular choice among amateur rocketry. So to discuss the custom flight computer, the SRAD flight computer, so this is based on STM32 hardware. That's a common microcontroller used in a lot of low-power applications. And it handles a couple different things. So first of all, the deployment of the primary recovery energetics, so sending those charges to the nose cone ejection and the tender descenders, but also data collection. So we have a number of sensors. We're collecting all sorts of different flight data that we can transmit back via our live telemetry system. So it arms its own systems. It also does some sort of the computation for the arming of the other systems, and also controls our camera for recording flight video. Some of the main sensors we have included here, so we have a barometric pressure sensor in addition to an accelerometer. We'll use those to determine our altitude with a high degree of reliability using basically sensor fusion. So we'll be taking the accelerometer to give us a dead reckoning so we can calculate where the rocket should be. But then the barometric pressure sensor will also allow us to sort of adjust that to prevent any drift or shift in our readings. Should allow us to be very precise with where the rocket is at any given point. We also have a gyroscope, a GPS module, and a magnetometer. The gyroscope tells us orientation, similar to the magnetometer as well, and the GPS module is used for tracking and recovery. To discuss our telemetry system, so the second, so the slides are slightly out of order, but the second board in the avionics space is our telemetry board. So both on the rocket and on the ground, we have the RFD 900. So on the rocket, it's called the UX. It's a smaller version. On the ground, it's a larger, more powerful modem. And this helps us to establish a roughly 902 to 915 megahertz radio frequency link, so we can communicate between the rocket and the ground. Gives us a range of approximately 40 kilometers. We did some testing last year, verified that up to a couple miles. We'll be doing more testing this year just to make sure it's even better. But we should have no problems with that. The data transfer rate, roughly up to about 125 kilobytes per second. We will not be anywhere close to that, so that gives us a ton of headroom on our system. I'll talk about this more in a bit, but all the data we transmitted is sent in discrete packets. So we're collecting data either on board the rocket or sending arming commands up from ground, and we will package those together and then send them in individual bits. And this allows for easy error detection, so we can determine if a packet has lost any sort of information in transit. Additionally, we have a backup tracking system. So there will actually be two of these. It will be the Altus Metrum GPS, and one of them will be on board the rocket, one of them will be in the recovery bag, as Trent will discuss in a minute. So the ground control software, this is a new development for this year. Last year we used software called Cosmos by Ball Aerospace. It worked fairly well. It was not quite tuned for our needs and lacked some customizability that we wanted in our design. So we wrote our own. And basically what this does is it's capable of graphing data, sending arming commands, receiving telemetry, and just also saving, exporting data. It just gives us a full vision of what's going on in the rocket. It's written primarily in Python in a packet protocol library, which basically handles the nitty-gritty parts of the communication, which was written in C. That same library is going to be almost exactly replicated on board the rocket. Again, data is stored in discrete packets for easy air checking, and it's currently open source under the GPL 3.0 license. So just to give kind of an image of the software as it stands currently, On the left here, we have our arming buttons, so we can click these. A confirmation dialog will show up where we can select to arm or disarm a system. We're plotting some important data points over here, so like altitude, acceleration, GPS ground speed, that sort of thing. On this main screen here, so this is tabbed, so we can set up different sort of viewers for different, different data points. Right here currently, so this is like our tracking page. So we have our altitude, acceleration, GPS. We can customize those however we want to display. Really any data point we're receiving, we can plot it. Over on the right, we have some more data printed out there, just additional information that we were collecting. This is something we're really proud of. We've had our team working super hard on this, and I think it's going to really help set us apart from the other teams as well. So our testing plan, there's a couple critical tests we'll be performing just to make sure everything works nominally. The first one is a vacuum chamber altitude measurement test specifically for our custom flight computer. We basically put the system in a vacuum and we depressurize it at approximately the same rate we'll be experiencing during flight as the rocket changes in altitude. It probably won't be exact, but it should help us validate whether or not our custom flight computer is going to deploy early, deploy on time, deploy late, or deploy not at all. So we really need to validate this new system as it's the first year we've done it, so this will be part of that. We'll also be doing some heat testing. There's stories of in the past how the avionics system might have just overheated and or the frame might have melted. So we just want to make sure that the system can withstand high temperatures that we might experience in the desert for extended periods of time. We'll be doing some injection tests where we hook up our system to the recovery system and make sure they're working well together. Additionally, I mentioned before, Payload has some magnets in their system, so we'll be putting them in the flight configuration, measuring all of our sensor data, monitoring voltages, currents throughout the system to make sure nothing is significantly affected. The test launch, of course, is a critical test for all of us. It just verifies the functionality of the entire system, making sure all the components are working. We'll also be doing range testing again with our radio, just to verify we'll be able to track it throughout the flight. And finally, software unit testing. So our software sort of sub team has been just making sure that we have full test coverage on all the code we're writing to make sure it will perform as intended. So some risks to the project success. The biggest one, if the flight computers do not fire the energetics, the rocket will crash. So we don't want that to happen. If the flight computers fire the energetics either early or late, the severity of this kind of depends on which point in the flight they fire. But in the most severe case, this could also result in the rocket crashing. In some cases, it might not be that big of a deal, but something we're going to be doing a lot of testing for. If the telemetry connection fails, either our own custom one or the commercial one, this is not a critical event, but it will make recovering the rocket a lot more difficult, if not impossible if it goes way off course. And then, again, so Payload is magnets, so if they interfere with either the magnetometer or any other flight computers, it might make some of our readings be slightly altered. Again, we'll be doing a ton of testing to verify that this will not be a concern. So here's our risk matrix here. This one here, so again, if the flight computers do not fire the energetics, that is very severe because the recovery system will not deploy. This should be rare. We're going to be doing a ton of testing with this. We have the test launch, we have our vacuum chamber testing, and then all of our good engineering and coding practices throughout, as well as the big thing, redundancy. So there's 2 flight computers, 2 recovery harnesses, separate systems that can, if one of them fails, the other one should still be functional. So the flight computer is firing early, so this is specifically a concern with the custom flight computer just because it's a new system we're developing. So lots of testing in our circuit design and our software design. We're designing it to reduce noise, which might affect our signals. On the software side, we'll be doing Kalman filtering with 2 data points. I mentioned before we have our accelerometer and our barometer. So we have 2 different data points. We're comparing the 2 to make sure we have the most accurate reading. And also we're looking to buy high-quality sensors that are accurate and will be able to distinguish between different points in the flight. So this, again, is slightly more likely, slightly less severe, still something to watch out for. if the telemetry connection fails. So that's possible. I know in the past we've had some issues with the radio link. So we'll be doing testing for that and also redundancy. There will be 2 trackers on the rocket and then 1 on the recovery nose cone. So redundancy again, and then testing for that. So the payload interfering with any of the components, but specifically the magnetometer. We'll be doing testing of this. If we can determine a relatively constant magnetic field from the payload, we can probably just correct for that in software and address that. So here's our schedule detailing what we've done throughout the year. In February now, we just have a tiny bit of board design left on the custom flight computer. The other boards are completely done. And same with the software. The ground software is just wrapping up some final testing. We're in the middle of our board assembly. We've assembled 2 of our boards. We have 2 more to do. And we're transitioning into microcontroller programming for all those boards. All throughout the year, we've been working and focusing on integration and subsystem testing. A big component of this is the software testing, which has been just going on throughout. So this is all building up to the test launch. After the test launch, we're going to evaluate, see if anything failed, see if we need to rework anything. If everything went well, we'll be just doing final testing and kind of cleaning and polishing things up. Any questions? Declan.
So in the event of a test launch failure, not necessarily for avionics, but in general for the craft or some of the hardware damage, would you go ahead and detail how, like, the turnaround time on getting new boards in place, getting new hardware in place?
Yes. We're a very design-intensive team. Probably 80% of our work this year has been in the design phase. Assembly or reassembly should not be too difficult. Ordering the circuit boards and getting them, all the boards themselves, the parts, the components in, we can do that in probably 3 weeks if we're committed to working overtime a little bit. So yeah, that's kind of something that works in our favor. All the design will be done by the test launch, so it's just a matter of just refabricating the boards. Yeah. Mm-hmm. Yeah, so for that, I'm sure Trent could tell you more about that. The custom flight computer probably will not be validated by the time of that, so we'll be using a commercial flight computer for the test drop. You can just keep going, yeah. Mm-hmm.
Yeah, so it's actually going to be in a pocket that's sewed on top of the recovery bag. That way, the nose cone doesn't interfere with the signals from the GPS.
On that note, one thing I should mention is for any of the antennas for both the GPS, the telemetry and all that, that's located in the transition piece, which is made out of fiberglass. So carbon fiber for the most part blocks radio waves, but fiberglass does not. So we have all of our antennas located down in there so we can still communicate. What do you have, Casey? Yeah. Yeah, so it's actually, we did that last year as well. So it's this, yeah, the smaller one is in the rocket and then the larger one is on the ground. So what wattage are you guys? We have, I'd have to check that. I don't know that off the top of my head. Mm-hmm. Yeah, I haven't actually ran those numbers yet. So one mitigation measure we took for that, because I was thinking about the heat, is the board which the radio is mounted to, it has nothing else on it. So it's an entire board about 10 centimeters by 10 centimeters with just the radio on it. And we have, in the board design itself, we added a whole bunch of extra vias which help spread out heat transfer throughout the board. But yeah, we'll check these specific numbers just to verify that. Yeah.
So you guys talked, so I understood the concerns for the relays we used last year, which ended up working out great. You mentioned that, you know, a physical relay can have worries for vibration safety. But then 2 bullets before we talked about adding a physical button, which I understand the motivation for. I heard you have a 2.5-second safeguard for press and hold. Do you have concerns or mitigations for inadvertently disarming computers in flight due to button bounce to acceleration?
Yeah, so that is, the mitigation measure for that is the press and hold, so it needs to be held continuously for 2.5 seconds, so any sort of slight vibration should not affect that. We don't expect it to. We could do some testing for that, but it seemed unlikely to us that the button would be accidentally pressed in that one state for a given amount of time. We could even just increase that time as well pretty easily. It's like 10 seconds or something.
Last thing, if I just go to the next slide. So I love the idea of the custom flight computer. So I know you're using sensor fusion with barometric and accelerometer data. I'm sure you're probably still kind of considering how that's going to go. We're ready to go for that. One thing I did hear is, do you have any thoughts or mitigations for barometric pressure data and Mach transitions? Subsonic, transonic, super, and back down is where you feel like they hit either lockout or second order filter, something else.
This is something, thank you for bringing that up. We'll definitely be looking into that, probably talking with Sawyer about the pressures we might experience at that time. Yeah, so we'll do some research and analysis with that. Possibly some sort of, in the code, we can look at it and see if we have some super anomalous results, we can favor, for example, the accelerometer instead at that stage of the flight, if we suspect that to be an issue. Yeah. Declan? Yeah, so obviously we're interfacing with recovery. We're sending them the electrical signals to deploy their charges. So there's 2 distinct harnesses. The harness is basically just a collection of wires, and those are mounted. Should have pointed out this earlier, but those are mounted to locking connectors on this bulkhead here, and they feed up through the recovery bulkhead to recovery. The reason we have them on this bulkhead is if for whatever reason there is some extreme or unexpected force on those, that'll be transferred through the aluminum structure of the bay rather than the circuit boards themselves. And again, those are 2 entirely isolated connectors for the main and redundant systems. Yes. Yeah. Yeah, so it's got the range of about 40 kilometers for that. So we can always look at adding, for example, heat sinks. We can look at redesigning the board it's mounted to. Oh wait, I'm going way in the wrong order. So this one here is, it's a surface mount component, so it's entirely touching the PCB. The one on the ground is actually on standoff, so it can have air flowing for convection cooling below it. If we think heat really is a concern, we could possibly switch to the larger radio on both sides to help mitigate that as well.
And then we do have a couple questions in the chat from Isaac. So question in terms of using the MOSFET for arming the COTS flight computer. Does the COTS flight computer have a separate power source? And if so, is it electrically isolated?
Yes, so the COTS flight computer, so it has a dedicated battery, which separate power source for the telemetrum. Yes, so all the boards normally are connected through the backplane to a large battery. The arming boards or the flight computer boards specifically have an additional battery. So that battery is used to power the flight computer, whether that be commercial or otherwise. And yeah, so that is electrically isolated. And if for whatever reason the main battery died, you know, just completely disconnected or whatever, the dedicated battery can still be used to power the flight computer as well as arming via the switch. So if the main battery dies, the RF link fails, whatever, we could still go in there and press that button, and that could arm it fully independently.
And then again from Isaac, did you ensure that the gate voltage and the MOSFET will allow for the high current voltage to connect charges?
Yeah, I don't remember the exact values over my head, but we verified those.
And then a side note from Gary, regarding the spaceport rules, or can you just talk a little bit about the spaceport rules regarding SRAD flight computers as the primaries?
Yeah, so my understanding was, as of checking a couple weeks ago, is they do allow for the SRAD computers to be the primary computer as long as you have a redundant commercial one.
And then also again from Isaac, how is the COS flight computer power source electrically isolated?
So basically how we have it set up is the commercial flight computer control power from two sources. The primary one being the dedicated backup battery, or sorry, dedicated battery for that. And there's a supervisor chip which allows us to also power it with the main larger battery. That battery is way bigger than it needs to be. So if we're sitting on the pad for I don't know, 6 hours or whatever, hopefully not, but we can supplement that power with the extra one. But primarily it is powered by its dedicated battery and does not require any other power source for that. All right. So I'll pass it off to Trent to discuss recovery.
Hello, my name is Trent Warner, and I'm the recovery lead. Our sub-team purpose, the purpose of recovery is to make sure that the deployment and the release of the recovery system is successful, and to reduce risks and improve our integration for launch day. Some system requirements. We need to have nose cone separation at apogee to then release our deployment system. After that, our drogue must maintain a descent speed around 75 to 150 feet per second between apogee and 1,500 feet. After that, we need the main chute to release, and the main chute must have a descent speed less than 30 feet per second until it reaches the ground. All right. An overview of the rocket. We are using a 1/4-inch shock cord. It's made of Kevlar and it's graded for 1,900 pounds. Some calculations I ran showed that this is more than enough. It gives around a factor of safety of 3. So I'm gonna point to these, but for people online, I'm just gonna give you the color. From the bag to the recovery bulkhead, it's gonna be 10 feet away, approximately 20 to 25 feet of shock cord. From the bag to the drogue, the green cord, there will be 15 feet of shock cord, and coming from the midpoint of that nose cone, from that bag to drogue chute line, there will be the nose cone line around 10 feet. Down at the bottom, you can see a picture of the system layout with the recovery bulkhead, shock cords, recovery bag, drogue, and nose cone. After the main release, then the bag will be removed, releasing the main chute, and it will be 2 separate systems. So we'll have 2 recoveries when we are out in the desert. Talking about the bulkheads that we will use, we have a single eye bolt that will be placed in the nose cone. With that, it'll just be drilled in and bolted to a bulkhead and epoxied around the edges to keep the nose cone attached to the system during drogue descent. And now the recovery bulkhead, this year it is it's more full than years past because we have 2 large ejection canisters that I will talk about shortly, 2 eye bolts, and a U-bolt. The U-bolt will be attached to the main chute, and the 2 eye bolts will be attached to the lines that connect that seal our recovery bag. And then there will also be a few holes that are drilled for our E-matches, our electrical wiring connected to our explosives to be charged. Those will be sealed off with either a sort of putty or tape to create a complete seal. Talking about the ejection canisters, this is a new design. They're much larger this year. They're around 4 inches tall. The point of that is to make it safer for like components such as the tender descenders, which I'll also talk about later, or just other components and wirings being further away from the explosives. We have decided to use 4 and 4.5 grams of black powder. The 4 grams will go off first, then the 4.5 will be used as a redundancy with a 3-second delay time. We've determined that 2 to 3 seconds is an appropriate delay time. And the testing shows that 4 grams will be satisfactory. You can see in the bottom right corner that this was our first test. We used 5 grams. That was more than enough. And then we ended up testing 3.5 grams, which was enough for a complete separation from the body tube, deployment bag, and nose cone. However, we do want to increase that just a little bit to make sure that when it's at a higher altitude, that the explosion will be enough to break the shear pins and release our system. So filling the black powder into the ejection canisters, they'll actually be in surgical tubing where the E-matches then are in direct contact with the black powder, and the tubes will be sealed shut, either with hot glue or tape. The surgical tubing is used to increase burning pressure for a more efficient combustion. In years past, we used gloves. I decided to go with surgical tubing because it's a little thicker, so hopefully we can get a more efficient explosion from that. Moving on to the main chute release. It starts with the deployment bag. This is a new design and something that we created this year. It's around 6 inches diameter, 14 inches length. It's made from double layer Kevlar/Nomex fabric, and there will be 6 grommets, 3/4 inch inner diameter, that are placed on the 4 flaps and 2 points here. This design is just a little out of date. We will not have grommets here that end up looping the shock cord through there because it causes a little bit too much friction. So we're just going to have 2 here at the top that overlap, and that will seal shut when the shock cord runs through it. There will also be Nomex fabric that is placed inside of the recovery bag to help reduce friction and protect the main chute from the shock cord that is looped through the recovery bag. We used a zigzag stitching for directional forces, and it's a very easy stitch to use on the sewing machines that we have. At the top of the bag, we have a GPS pouch that we will make. It's at the top of the bag so that it's the safest spot for it, because the top of the bag here on the bottom right, where that black loop is, that will be around where it is. It won't have it'll be the furthest distance away from the explosives, and it should not face any forces or violent like shakes under descent. All right, now this part is how we will end up releasing the shock cord system from the recovery bag. We will have two tender descenders placed in parallel, and that will be connected with a machine part here. You can see there will be a sew loop here you can see on the white tape. This will end up being sewed. So it'll be fully encased when the tender descenders are closed. However, when one is fired, the system will swing open, releasing one side. There's two for redundancy, so if one fires and it does not release, the other one will fire, swing open, and let our shock cord follow through the system. So yeah, so going back, once the tender descender are fired, the force will still be pulling up from the drogue chute, causing the shock cord line to run through these Kevlar sleeves. The Kevlar sleeves are put into place to protect against shearing against the walls of the body tube or nose cone. But also here, there will be a tiny bit sewed at the top and the bottom of Kevlar, the Kevlar sleeves. This is to help guide the shock cord to prevent tangling issues or, because tangling is a really big problem. So this is one of the ideas we came up with to help stop that. So once the shock cord is pulled through the bag, it'll still be connected to the main cord, which is connected to the U-bolt in the center of the recovery bulkhead. The bag will be pulled away for the main chute to then catch the wind and start the main descent. This year we're using an 18-foot parachute. Under main descent, it should be around 15 feet per second. We're using ripstop nylon, and there won't be any spill hole on it, as opposed to the 4-foot drogue chute, which will, when it's under, I actually apologize, this is in reference to, the 17 feet per second is in reference to the separate nose cone drogue system. The drogue deployment will actually be around 75 feet per second. This is made out of ripstop nylon, and there's a spill hole in this one. So our test launch coming up in April, we will use that to help verify drag predictions and speeds during our descent. And we hopefully, I will talk about this again in a moment, have a drop test out of a plane to test the parachute deployment time and see any problems that might arise. We're continuing ejection testing. We've already ran some for the bulkheads and the separation of the system, making sure the shear pins shear and the nose cone ejects. And then we also have another test that I'll talk about right now. The tender descender testing, we tested just the tender descenders themselves, make sure that they work, they pop off. And next meeting, I plan on having the tender descender system tested when it's under tension from the drogue chute. So we'll rig up a system, put it under some force to verify the tender descenders can still fire, and then the system will release. This is something I've been really excited about. I wanted to do a drop test to test out the deployment of the recovery system without risking any other subteams, components, or parts. So for this, I've been talking to the skydiving instructor at OSU, and I should be meeting with him in a few days where he will look over the system and we will talk about the drop test, which will hopefully be happening in a few weeks if everything goes according to plan. For the mock system, we're going to use a nose cone and body tube that were made in like past years or this year that weren't quite up to standard. So there were just some parts lying around that are good enough for the test, but we definitely didn't want to take to Spaceport. We will end up using a basic flight computer. We don't need too much. All we need to do is fire the tender descenders, because we will be simulating post-ejection test. I just felt this was easier because I didn't want to cause an issue with bringing extra black powder into a plane. And it will be the current recovery system that is going to simulate the real flight. I feel like all my risks are pretty high. So some risk being the tender descenders do not release. We have 2 of those for redundancy, and we are doing testing. We've done testing to verify that they will fire. The parachute does not come out of the bag. We are performing the drop test in a couple weeks, hopefully, and we have separate systems like our divided Kevlar sleeves to help guide the shock cords, and also going back to like the bag, we're using grommet sizes that are more than big enough or more than wide enough to feed our shock cord through without problem. Another issue is the main/drogue becomes tangled. We just have to be careful with our folding patterns and how we put it into the bag and body tube. But that should be all right. And finally, the ejection charges do not fire. We have 2 of those for redundancy as well. And we will use like safe wiring configurations to make sure that they don't risk of getting pulled out or sheared or anything like that. For the rest of the year, we're still building the drop test system that we plan on using in a couple weeks. We're doing ejection testing as well. There's still parts. We're pretty confident on the amount of gunpowder, or black powder, I apologize. I've probably said that a few times. Black powder we'll be using, but we still want to make sure that structurally it will withstand loads. Then after that, it comes to test launch. And then you can see that between the test launch and June, there's really nothing going on. That's if everything goes according to plan, which it probably won't. If it does, I'll probably use that time to build second systems, a second bag in case something goes wrong. And if something like the drop test or test launch fail in some way, shape, or form, I'll use that time to rebuild everything. Any questions? Liv?
So you mentioned that your main and body tube are coming down one, and then your drogue and those kind of coming down separately?
Yes.
For 2 recoveries. Can you elaborate why you want to do that?
So the reason for 2 separate recoveries, I felt it would be simpler if they were separated, because I was a little scared of tangling or nose cone getting like interfered with something. I just wanted them to be separate so I didn't have to think about all the cords possibly interfering with each other. And it didn't seem like it was too much of an issue, as we just have to add an extra GPS to the recovery bag.
Okay, and so obviously everything goes up together,
Mhm.
and it has to start coming down with the drogue together. It's when the main deploys that they separate?
Yeah, so the main chute is inside the deployment bag, and once the bag is no longer in tension, the drogue will keep pulling up on the bag, and eventually the cord from the main will still be attached to the body tube, and then the bag will the chute will be pulled from the bag, and then that's when it'll separate. Yes. Declan?
Follow up on that, do you have any sort of like estimate on how far apart you think they're gonna land, in terms of like distance from 200 feet to 0?
Well, I don't think it will be too far. I have no idea, but I will say this deployment might be a little bit slower than other deployment systems. So if it starts at 1,500 feet, it'll still be falling for a little bit before the whole system deploys, if everything goes according to plan. And I'll probably be out in the desert too. So it'll be a fun little experiment to see how far away they fly. Yes?
So you mentioned, so because of this like dual recovery system, that GPS is on the bag,
Mm-hmm.
really important
Yeah.
Are you planning on doing any ejection tests with that GPS integrated into that? You mentioned it's not integrated yet.
Currently, I do not, because we'll be trying to think. I would like to. I'll see if we have enough time for it. It would be nice, but I think it's a timing issue right now. Yeah. Is there anything else? Did I answer that? Okay. Yeah.
How does the recovery system interact with test launch insofar as the height limit being a lot shorter, and the motor being
I believe we're still gonna fire this, like, release the system at 1,500 feet, right? Okay. I don't think the height difference matters too much. It just changes how long the system is under drogue descent. Yes? No, when I talk to him in person and show him the whole system, that's when I plan on asking some of those questions. Also, like, you know, how many people I'm allowed to bring in the plane, stuff like that. Yeah. So I believe 1,500 feet is the max that they allow you to fire the deployment or the system. And I do believe that it might take our system a little bit longer than others to deploy. So I feel like starting at one of the higher points gives us more than enough time to release the whole system. No. Mm-hmm. Yeah, sorry, I didn't, off the top of my head, I don't have the exact shear pin, but we're using the same shear pins we were using for the testing, including the ones where I used 3.5 grams and 5 grams of gunpowder, black powder, and they were fully sheared. You keep going.
So I like the innovation on the new recovery system and everything. One concern, so I see that chopped rudder, or whatever you want to do, extra cord has to snake its way through that Kevlar sheet and then through your grommets.
Yeah, so friction. Yeah.
So have you done, so could you do a test on the ground, like just having someone pull on the bag?
So I had this system where you could, I don't know if you can actually, that's a bad picture. So down here on the right, this is what we had set up at one point, and I was able to pull it, but I had to use some force. I ended up throwing some weights on there, and it was about 20 pounds, so that was way too much, like way too much force that I needed to use. So that's why we're gonna end up not end up using some of these grommets up here, and it will just be a loop that goes up through the bag and then out the other side. So it'll almost be just like I don't know, a single point kind of that it's coming in contact with. And I still need to do that to test how much force is needed to remove that. Yeah.
And I guess real quick, just because it's a safety related thing.
Mm-hmm.
You said you're using flight computers for that ground test, is that the plan?
Yeah, we'll use some of the longer.
You're not gonna use the apogee deployment setting, right? You're gonna use the game wants to. Or you have a plan B? Not exactly the same as rocket.
We also have like a,
To make sure the flight computer
All right. Mark?
So you mentioned the sealing of the wire hole in the bulkhead.
Yeah.
You said you're using putty or tape.
Yeah, like, I haven't looked too far into that, but I just figured that would be enough to make sure that there's no pressure leaks or anything like that.
Yes, last year we used hot glue, so that's something.
Yeah, I'll definitely consider that. Thank you.
And then you said that the bag is 6 inches in diameter.
Yeah, so we did test it, like when we used our 3.5 gram ejection testing. I'm pretty sure it's kind of hard with the fabric and all to measure it. But when we were able to compress it into the body and the nose cone with some force, but nothing of too much an issue. Yeah. 6 inch, I can't say exactly what it is, but it is like maybe 5.5 to like 6.2, if I had to give you like a random guess, kind of.
Yeah, I thought that was just making sure.
Yeah.
And then I think you said there's going to be a 3-second delay
Yes.
on the tender descent.
Yeah, so, yeah, so there's gonna be a 3-second delay. Actually, I do wanna go back up to the other one because I wanna show you the piece. Right here, yeah. So this piece is in between the two tender descenders, and this, the shock cord that will be sewed here into a loop will be in the middle here. And there's a 3-second delay because I just feel like that will be enough time to fully allow, if it does fire, the cord to swing, or this to swing open and the cord to pull through.
Are you seeing like delays between the tender, like one tender?
Yes, the delay is, yes, sorry.
And then, do you have an estimate of how long the separation would take for, like, from when those fire to the like fully descent under the main point?
No, that is more so for the drop test to help determine. I don't really have I guess we could like set up a test, but then again, I don't know the exact like timing it even takes the main to deploy once it's fully separated from the body, or the bag, sorry.
And do you have do you know descent rate under the nose?
I believe around 75 feet per second. I'm gonna have to double check because I was also toying around with the notion of changing the drogue chute just so that there is more force getting pulled on the bag once the tender descenders release.
Yeah, 'cause, like, my thought there is, I guess under worst case, have the 3-second delay.
Mm-hmm.
I don't know, maybe say 3 seconds to release the main, if they were fully main descent.
Yeah.
At 75 feet per second.
Yes.
That's gonna be a lot of feet.
Yeah, it is like it is a lot of time to fully deploy. That is why we're also gonna deploy at 1500 to give ourselves the most time for full deployment.
That's just something about that. And then on your testing, you said that the test launch would be able to verify drag parameters. Do you come out with a prediction of what parameters you're looking at?
I guess just to verify like some of the descent speeds calculations, because sometimes I'm just going off of drag calculations based on parachutes, and I don't know exactly how well they're going to correlate to like the calculations. And I hope to only use the test launch for that. I want the drop test to test like more important things when other people's like components and parts aren't being used. All right.
There would be a quick one from Gary in the chat.
Cool.
So your linkage between the tender descenders,
Yeah.
is that tethered up to anything to prevent free fall after they fire, or will that just fall by itself?
This part or the tender descenders?
Your linkage.
This thing?
Yes.
Yeah, so we're actually gonna just take a tiny drill bit and probably drill at some point down here, and we'll just loop a tiny thread through there. Oh. I'm thinking real quick, sorry. Yeah, our plan was just to tie like a tiny loop through each side. I can see that there's gonna be a problem though with one of those pieces. Probably have it. I'm gonna have to look into that, but the original plan was just to tie like a thin thread through the system. Is any other questions? Cool. All right.
Laser pointer, back and forth, there we go. All right, I'm Adam, I'm the payload lead, and I didn't put the motto on here, but our motto in payload is throwing things on springs, because favorite machine element. All right, let's get going. So the payload purpose is to design and manufacture a bay with the 3U CubeSat form factor. I can't remember if I talk about it later in the presentation or not, so I'll talk about it now. 3U CubeSat just means it's 10 by 10 centimeters by 10 centimeters at the base, 30 centimeters tall. Well, 10 centimeters tall for 1U. We're doing 3Us, so 30 centimeters tall. That would go in an actual satellite. They changed the dimensions a little bit this year, so instead of using the ones that go in a real satellite, we use the actual 10 by 10 by 30. So we'll talk more about that later. So the goal of this experiment is to generate electricity from the rocket motor, and we're going to use that electricity to track the motion of our oscillator, and we'll talk more about that later. And we're also going to incorporate an outreach payload into our own teams. So the requirements of the system is it has to be self-contained. None of us really wanted a separate recovery for a payload, which is allowed. I learned that for the first time this year. We cannot alter the rocket's flight path. That's a competition rule. It's got to fit in the 3U form factor. And the total weight must be 8.8 pounds. The minimum weight for the competition is 8.8, but we want to be right around the 8.8 margin. So the generator itself generates electricity consistent. Our goal is to generate electricity consistent with our simulations to track the movement of the oscillating system. So this whole assembly is 140 some parts, so this is just the aggregate system. Basically, there's a magnet in here, a neodymium magnet, I believe it's pronounced, sandwiched between two concrete block cylinders to make it heavier. Corey likes it when I say pucks, I like cylinders. And as that moves through a coil, that's on two conical compression springs. As that moves through this coil, it induces a voltage consistent with Faraday's law. Change in flux over change in time, if you remember. So all the mounting fixtures on this are going to be printed from 3D printed from ABS plastic. Most of the stuff in this are almost impossible to machine. And the voltage generated is directly proportional to the mass of the oscillator and the number of coils. So that's why we sandwiched it between the concrete so it oscillates faster. Yeah. And we were using 1/8 inch diameter wire, I think. We switched to 1/16 so we can double up our coils. And that should get us around 0.2 volts. And we're going to measure this voltage with a Raspberry Pi circuit. So the payload team consists of me, a mechanical engineer, MSE, material science engineer, and 2 aero engineers. So none of us really know how to do electronics. So Peter is going to help us out with measuring that. And so the actual CubeSat, we were going to make this out of stainless steel. A lot has changed about this since the beginning of the year because of a lot of administration problems, manufacturing problems. So we're going to make it out of mild steel, and we're going to weld it. We were originally going to tap it and screw it in. It's too much. We can't do it anymore. We're running out of time. We got to get this thing machined. So to make it easier to weld, we're going to cut slots in these struts, and the corners of these plates are going to go in the slots, and then it'll be easy to weld on there. And Aaron Osborne from the machine shop over there is going to do that for us for free. And these face plates we're gonna have them outsourced to send, cut, send. I'm waiting for that order to get placed. Basically, you just send them a 2D picture, and they will laser cut anything you want in the correct dimensions. It's great. I think it's going to cost us $30 to get 4 of these. If we would do it ourselves, the material for one plate would be $90. So send, cut, send is a great option. The outreach experiment, so the goal of the outreach experiment is to measure the state of matter of a non-Newtonian fluid. Let's talk about outreach really quickly. So when I say outreach, I'm referring to Metro High School. Sarah Malaska set up a program, so to speak, whereby we go to Metro High School on, I think we did Thursday mornings, and then we gave them a design challenge. So basically, they got to pick an experiment to run in the rocket, and there were groups that made several different experiments. We picked this one because we thought it was most interesting and feasible. And that was tracking the state of matter of non-Newtonian solid. Originally, they wanted us to use a sensor that was around $10,000, so instead, instead of measuring the state of matter directly, we're going to mount, so basically, this cap goes on top of this box, and then it looks like this. But there's a slot in here for a force-sensing resistor on which we're going to put a spring, my favorite machine element. So this box is going to be filled with a non-Newtonian fluid. We're going to dip the spring in there, and the idea is that a large force indicates that the non-Newtonian fluid is turning into a solid and interfering with the coils on the spring, pulling it downwards. If it's a fluid, it should have practically no effect on it. And everything on here is going to be printed from ABS plastic. Test plan, we're going to verify the magnet doesn't interfere with avionics. My idea was to just assemble the ISB, induced magnetic field, and see what happens to avionics. There's Peter talked about it earlier, it's just solid state stuff. The only thing that could be messed with, in theory, is the magnetometer, which I was told is just on there for fun. We'll try to keep it non-interfering though. And also for us, we're going to conduct a low voltage test on the ground and compare it to our simulations. So risk project success, our springs could not fail due to loading. This would result in our spring constants not being consistent with our simulations. They would vary with time. Right now it's constant spring rate. We've predicted some preliminary measurements we predicted a factor of safety of 1.2. We need to update that. It's still right around that margin. We're getting the McMaster car rating says it's rated for 9 pounds, but we've been testing them greater than 10 pounds and they've been fine so far. The spring constant's the same. There's been no yielding. Because the magnets are brittle, we could have them fracture during flight or assembly. During some tests, we've already had a few small magnets fracture, but not the big one that we're using. To be honest, I'm not entirely certain what would happen, but I'm pretty sure the magnetic field would not be consistent anymore. We don't want it to happen. Wires could come loose, and that would prevent us from collecting data. And 3D printing mounting hardware could fracture, which would result in the failure of the payload experiment because there would be no way to hold it in place so it could oscillate. For the risk matrix, I always forget when I fill out of this risk matrix, severe to me means not the rocket failing, it means my payload failing. So this presents practically no risk to the rocket in general. So if the springs were to fail, well, springs failing would be bad, but unlikely. As I said, we've already been testing them past their rated, their conservative rating on the MasterCard, and they've been doing fine. But we're going to test those even more. The next one would be magnet fracturing during flight. We're going to have backup magnet, maybe two, and we've got a bunch of extra silicone so we can cushion the magnet between the concrete blocks. Also, we're going to make sure it's tightened down in the assembly pretty well because we don't want it to jiggle in the oscillating cap. That would increase the likelihood of the magnet fracturing. If the wire's coming loose, we can prevent that by soldering the wires or using connectors. Again, I'll refer to Peter's advice on everything electronic. He'll probably tell me to use connectors. Oh, by the way, everything except for the springs failing would be a severe problem for the payload. If printed mounting hardware fractured, severe problem. We're going to print it with ABS, and we're going to test the hardware under the expected loading. There's been some arguing as to whether or not our prints will survive. I think they will. Basically, we're going to put the magnet. Sorry, we're going to fix the spring onto the mount, and we're going to load it using gravity with a bunch of weights we have at the CDME. Schedule. So we've been trying to manufacture. The payload bay was supposed to be manufactured last semester, like long ago last semester. So I need to get this order into send, cut, send. I'm going to be bugging finance about it this week, and probably Dr. Horak. So assembling payload experiments. I've already, at the last meeting I calibrated, I think the only sensor we're using that Peter's not developing for us. So now we're just waiting for stuff to assemble. We're going to test the payload experiment and make any necessary refinements. The electronics are kind of up in the air because I'm not doing it. So, yeah. Any questions? Declan.
So, you mentioned that the safety factor 1.2 is the springs were yielding.
Yes.
Do you have a factor of safety for the springs actually failing completely or breaking?
No. You're talking about fracturing steel. You would probably have to put over 100 pounds on it. The yielding is around 10 pounds.
Okay, what is the mounting? So I guess where's the weak point in that system? So in terms of, would it be more likely that the springs might disconnect from the frame or from the magnet? Have you factor safety there?
We haven't tested the factor of safety yet because we don't have the payload bay. We should be able to get some kind of mount set up to test this. We'll probably be doing that at the next meeting. I think the maximum weight we're going to have on it is 10 pounds per spring. So roughly 10, 12 pounds pulling on that. That is the weak point right there, that cap. The spring is sandwiched in between two of these caps, and it's kind of thin plastic. That's where the worry's coming from. So we will have a factor of safety on that soon. I don't know if we'll actually get it fully to failure, but we'll figure out if it's going to survive our loading. Anybody else? Declan.
So you mentioned you wanted to take the current and voltage current induced by the magnet and track that against the position of the magnet. So what is your setup for measuring the position of the magnet?
I'm glad you brought that up because I forgot to mention it. So we're using a neural net. This is Corey's brainchild. I don't really understand neural nets very well. We're basically going to have a camera inside the payload bay pointed at this system, and it's going to watch the position of this. And the neural net is going to tell us its deflection with respect to time. And once we recover that, we're going to take that data. We're going to take that data that video gives us, presumably, and we're going to compare it to what our simulations say. Because our simulations, it basically takes the voltage, tells us how fast it was going, where it was going, acceleration, all that stuff. So a neural net with a camera.
Follow up on that, so you have to be electrically disconnected from avionics.
Yes.
Part of your system. So for a camera to be running, do you have any concerns about how long the camera can be running sitting on a pad? Do you have a way to arm or disarm the camera so that you're not using the battery? And what do you have as far as battery life for that to make a communicate?
I plan on, if I can, I plan on running everything off an Arduino, except for Peter's stuff. We're doing a Raspberry Pi. I've been told that's easy to program on as well, so I might run it off. Oh, yeah, we've got plenty of room. Push comes to shove, I'll put a drill battery in there. That'll last for hours. Anybody else? Casey.
So I know we talked a little bit about the springs failing either due to the elastic deformation or troubleshoot fueling. I know you said that there's no risk to the vehicle, but if your magnet system were to come crashing down into that bottom bulkhead, if that bulkhead failed and you went to the avionics bay, you mess something up there,
We're putting panels on the sides, so it would land on the panels. Nah. Oh, yeah. Yeah, it could happen, but we're going to have the thing surrounded in panels, so probably should put that on my risk matrix.
second question, so you're talking about you're going to generate on the slide actually 0.2 volts. EMF is just a measure of potential, so do you have any idea how much energy you're going to generate, amperage, or
Probably a Peter question. If I had to guess, I would take the total resistance of the wire and divide that 0.2 volts by the resistance of the wire, and that would give us a max amperage, I think.
For this, my understanding was the tool is not to generate electricity, just to measure the voltage. The power will be very low, so that signal is going into an analog digital converter, and the mouse can't push that theoretically, because obviously not that indicator, but yeah, the power and the current section is very low. So we're really just looking at the voltages at the ground.
This payload is more of a proof of concept. Most generators, have a lot of spinning action, not oscillation action. So if we get good data back, theoretically, you could scale this up and get a lot more electricity. Anybody else? Anybody online? All right.
All right, so thank you, everyone. Good job, all my leads. Now we're going to open the floor just for any last questions regarding any of the previous systems we covered or just the entire vehicle in general, either on the YouTube live stream chat or anyone else out in the crowd. What you got, Casey?
So you're increasing the length of the motor, right?
Yes.
66 inches. Do you have any plans for, so I know test flight is a systems validation, and NASA and subscale is used in similar ways to validate, attempts to validate aerodynamic performance of the vehicle, and clearly subscale version. With that increase in motor tube length, do you have any plans to increase the length of your carbon motor tube that you use for test flights?
No, we're not. We're primarily keeping that the same, just because that tube worked really well for us, and we don't really want to spend too much time kind of reworking that. Like Ethan did mention, we are going to increase the diameter just by adding that thickness, but in terms of just length, no, we're not changing that. So we also are running open rocket simulations for the test setup to make sure that we're stable kind of in both conditions for the test launch and the competition launch. So. Anything else? Anything in chat? Alrighty, well, if that's all we got, then this will conclude our critical design review. So thank you all for coming. We're hoping it'll be a kind of good closeout to the rest of the year, and we'll kind of keep doing some good work and hopefully do well in competition. So thank you.